Hey, good afternoon everyone. In today's video, we're going to go ahead and we're going to talk about something called the Laplace equation. And the Laplace equation is kind of an odd equation in that it's different than the heat equation and the wave equation. What the Laplace equation is it's a partial differential equation that takes place over a space domain as opposed to just both space and time, or position and time. And really the gist of the Laplace equation goes a little something like this. The way that I've had it described to me and the way that I tend to interpret the solution of the Laplace equation goes a little something like this. So imagine that you have perhaps like a sheet stretched relatively tightly over a mattress or some sort of a surface. And pretend that you take three ends of the sheet. The three ends is kind of arbitrary, but for our purposes, it's going to make a little more sense if we just do it with the three ends. So we hold the three ends of the sheet down, or three sides of the sheet down. So our sheets pin down along these three sides. And let's pretend that we can go ahead and perhaps deform the fourth side. So maybe the fourth side of our sheet looks something like this right here. Now, the question is, what will the rest of the sheet look like based upon these, let's call them boundary conditions, because they're really describing what's happening on the boundary of our sheet. And really just intuitively, we can kind of see what our sheet's probably going to do. So if we start up here at this peak and kind of run straight to the back, probably going to decline like that. Or if we start down here at this valley, we're probably going to increase up there. And then somehow along our sheet, we're going to dip up, dip back down, and then go up like that. So we can kind of visualize what our sheet is actually going to deform into. But the question is, how do we turn that into a mathematical equation and get the solution as a mathematical expression? And it's simple, but it's also kind of a difficult thing to be tasked with, right? So I'm going to give a very quick explanation of kind of how I visualize the Laplace equation. This isn't the true derivation of the Laplace equation, and it's not really the best interpretation of the Laplace equation. It's not the most accurate interpretation of the Laplace equation, I should say. But one way that you can think about it is if you were to grab a point somewhere on your surface and think about what you want to happen on that surface if you want it to deform nice and continuously, nice and smoothly. Well, what you would really want is you would want the slope at that point in both directions, so in your x direction and your y direction, to perhaps be as small as it can possibly be, right? You don't want it to be like a real steep peak somewhere in the middle of your nice smooth sheet, and you don't want any like real overly steep areas across your sheet. So one way that you can kind of think about this, right? It's not entirely accurate, but you can almost think of the slope at this point as being somehow related to the partial derivative of our surface. We'll call our surface u, and we'll call u a function of both x and t, with respect to x, plus our partial derivative of u with not t, y. We're in space here. Plus our partial derivative of u with respect to y. Right? So you can kind of think about this as being the slope of the surface at that point. I know it's not entirely true, but for our purposes, that's just the way that we're going to think of it. Right? So what we really want to do is we really want to minimize slope. Meaning we don't want any steep peaks or points or cusps or strange things happening on our sheet, if we want to think about it as a sheet. So what we'll do to minimize slope is we'll take another derivative of our slope function and set it equal to 0. So again, this is not entirely the best way to think about this, but it's a pretty easy way to get to the Laplace equation. So if we take another derivative, well, we'll take our second derivative of u with respect to x, and then we'll take a second derivative of u with respect to y. Add those together, we'll call that our derivative of our slope function, and we'll set this equal to 0. This right here is what we're going to call the Laplace equation. So we'll either state it like this, or we might just state it like u sub xx plus u sub yy equals 0. And either one of these are what we're going to call the Laplace equation. All right, so now there's a couple different ways to think about how we solve the Laplace equation. or how we set up a Laplace equation. So let's come up with a Laplace equation example, and let's just quickly run through the solution. Quickly might be a little bit of a stretch, but we'll run through the solution. So let's start an example. So we'll solve the Laplace equation. Subject to some boundary conditions. So notice now in the Laplace equation, we're not going to have initial conditions because we're not time dependent. We're purely space dependent. So all of our conditions are going to be boundary conditions. So we'll have something like, let's say u of, let's go x0 equals 0. So we can almost think about this as holding the back of our sheet equal to 0. We could do something like u of 0y equals 0. This would be akin to holding the left side of our sheet equal to 0. Let's do something like u of ly equal to 0. This would be holding the right sheet of our or the right side of our sheet equal to 0. And then let's go ahead and let's do something like this. Let's say we have u of x comma l equal to a function of x. So this is what we're going to think about as holding the front face of our sheet along some sort of a curve. So we're going to deform the front face of our sheet. And basically what we're setting up is we're setting up exactly this, right? So we're almost imagining as this being our origin. Then we're coming out to this point here, which would be 0 on the x-axis, L on the y-axis. This point out here would be the point L0, and then this point right here, we'll call this the point LL. So pretend that we're living on a square sheet. It doesn't necessarily have to be square, but to make things a little bit easier, we'll just make it square. All right, so the way that this is going to work is we are going to jump into it and we're going to start solving it the same way that we started the heat equation, the same way that we started the wave equation. So we're going to start with a pretty simple assumption. So we're going to assume that the solution is going to look like a function of x times a function of y. We'll take our partial derivatives, we'll substitute them back in. So here we'll have an x double prime y plus an x y double prime equals 0. Here we can go ahead and we can separate our variables. So we'll be left with an x double prime y equals negative x y double prime equals 0. I will say that since all of the differential equations that we've really tinkered with up to this point, we've always had a positive x. So let's go ahead and let's keep that negative sign associated with our y value. And I'm going to write this in kind of a particular way. We'll see why here in a moment. So I'm going to leave my x terms positive. So I'm going to divide both sides by positive x. And then I'm going to divide both sides by y. And I'm going to write y double prime over y as y double prime divided by negative y. And that's not going to be equal to 0. Notice now we have a function of x on the left side, a function of y on the right side. So these both have to be equal to some constant. We'll call that constant lambda. So now we can go ahead and we can turn this into two differential equations, or two ordinary differential equations. So we can take the first grouping of x double prime over x being equal to lambda, and we could write that as an x double prime minus lambda x equals 0. And we can write our second grouping as y double prime. Notice now we have this minus sign down here, so that's going to change the sign on lambda. So we'll have a plus lambda y equals 0. So now let's go ahead and let's think about what our boundary conditions are. All right. So normally we only have boundary conditions in x, but this time we have boundary conditions in x and y. So we have two second order differential equations, and we have 4 boundary conditions, 3 of which are 0. So we really want to solve the differential equation with the simplest boundary conditions to apply first. and then we'll apply the remaining boundary conditions to our other differential equation if we can do that. So let's go ahead and let's take a look at what our boundary conditions are. So u of x0 was equal to 0. So let's think about what that looks like after we apply our assumption of what the solution is going to look like. So this basically says u of x0 is going to be x of x times y of 0 equals 0. So this tells me that y of 0 should be 0. Okay. Our second boundary condition says u of 0y should be 0. So here we're replacing x with 0, and we're leaving y alone. So this is going to be x of 0 times y of y equals 0. So here we get that x of 0 should in fact be 0. Next we have u of ly equals 0. Well, that's going to be x of l, y of y equals 0. So here we get x of l equals 0. Right. And then our final boundary condition, since it's not equal to 0, we really can't think about applying it yet. So we'll have to come back to that a bit later. So what do we have? We have y of 0 equals 0, we have x of 0 equals 0, and x of l equals 0. So since we have a second order differential equation in x and two boundary conditions that we can immediately apply in x, let's go ahead and let's solve our differential equation in x first, right? So we'll solve x double prime minus lambda x equals 0, and that's subject to x of 0 equals 0 and x of l equals 0. Well, fortunately for us, this is a differential equation that we've solved about a dozen times already, right? So if we went through and we wrote down the characteristic equation, solved the characteristic equation, then went through the three cases of lambda, lambda being positive, lambda being 0, and lambda being negative, we would find that positive values of lambda and lambda equals 0 yield trivial solutions, which we don't necessarily want. So the only solution to this is going to be when lambda is negative, and in particular, our values of lambda are going to be negative n squared, pi squared over L squared. So we'll call those lambda sub n's, and our eigenfunctions in x will be x sub n equals some c sub n's times sine of n pi over L times x. So we've got our eigenvalues, we've got our eigenfunctions in x down, right? So that takes care of the entire part of the x differential equation with the x boundary conditions, right? So let's go ahead and let's take that value of lambda, let's plug it back into our y differential equation and see what we end up with in y, right? So our y differential equation, remember, was y double prime plus lambda y equals 0. And the only boundary condition we had on y so far was y of 0 equals 0. All right, so what was lambda? Well, lambda we said was negative n squared pi squared over L squared. So we can go ahead and we can substitute that back in. And what we end up with here is we end up with two different solutions to the characteristic equation, positive n pi over L and negative n pi over L. Right? So here we're going to end up with y of y is going to look something like, we already used c, so let's use d, a d sub n times e to the n pi over L times y plus, let's do a p sub n e to the negative n pi over L times y. Now, if we go ahead and we apply our boundary condition, we know that y of 0 is going to be equal to 0. Well, what do we get if we plug in 0? We just get d sub n plus p sub n. Right? So that means p sub n is negative d sub n. All right, so what in the heck does this tell us about everything? Well, now we can write down what y of y is. So y of y is going to look something like a d sub n times e to the n pi over L times y minus e to the negative n pi over L times y. All right. So we can go ahead and we can tie all of this back together. So if we remember what x was, x of x was some c sub n times sine of n pi over L times x. And we have our y of y. I'll take that even a step further, and I'll call that a y sub n of y. So we can go ahead and we can write down our u sub n of x and y. It's going to look something like a c sub n sine of n pi over L times x times y of y. So that's our d sub n times e to the n pi over L times y minus e to the negative n pi over L times y. And finally, we have the c sub n times this d sub n. We can combine those into just one coefficient. We could call that b sub n if we would like. And we can finally state what u of xy is going to be equal to. So we're going to add up all of the solutions for every value of n. So n started at 1, it's going to increase to infinity. I'll combine my c sub n and my d sub n into something that I'll call a b sub n. So we'll have our solution is going to be a b sub n times sine of n pi over L times x times this quantity e to the n pi over L times y minus e to the negative n pi over L times y. And finally, we're at this point where we can apply our fourth and final boundary condition. So we'll have, sorry, let me remind myself what my fourth and final boundary condition was. U of xl equals f of x. So this time we're plugging in an L for y and we're leaving x alone. So this is going to be the sum from n equals 1 to infinity of these b sub n's times sine of n pi over L times x times, here we're plugging in L for y, so we'll have e to the n pi minus e to the negative n pi. All right. So what we have here is we do have a function expressed as a Fourier sine series, where the coefficients b sub n times e to the n pi minus e to the negative n pi. So our coefficients are going to be equal to, well, since y is varying from 0 to L, this will be a 1 over L, sorry, a 2 over L integral from 0 to L of our function f of x times sine of n pi over L times x and dx. So we can finally solve for our b sub n. Is going to be 2 over L times e to the n pi minus e to the negative n pi times the integral from 0 to L of f of x sine of n pi over L times x dx. So there we have our solution to the Laplace equation. It is that function, the sum from n equals 1 to infinity of sine of n pi over L times e to the n pi over y minus e to the negative n pi over L times y, where our b sub n's are these values here. So for a given a function that represents the deformation of the one side of our sheet. This is the solution to the Laplace equation. So I'm going to go ahead and leave it there. Hopefully you got a little something out of this. If you do have any questions, feel free to leave them down below in the comments. Otherwise, have a good day, and we'll catch you in the next one.